Early 1945. The waters off Japan's coast. An American F4U Corsair ditched after engine failure during combat operations, the pilot ejecting as the fighter hit the cold Pacific. Within hours, Japanese patrol boats converged on the floating wreckage. What they recovered would become one of the most significant intelligence opportunities of the war's final months. For nearly 3 years, Japanese pilots had faced this American fighter in the skies over the Solomon Islands, Rabaul, the Philippines, and now the home islands. They had learned to respect its speed, its firepower, and its seemingly indestructible construction. But never before had they possessed an intact example to examine in detail, to measure, to test, and to understand how far behind they had fallen. The story of Japan's encounter with the F4U Corsair is not merely a tale of captured aircraft. It is the chronicle of a nation's technological awakening, the moment when Japan's aviation specialists confronted the full magnitude of American industrial and engineering superiority. Through examination of this fighter, they would discover truths about manufacturing precision, materials science, and design philosophy that shattered assumptions about their own capabilities. The Corsair that Japanese salvage crews recovered represented the culmination of American fighter development. Designed in 1938 to meet the United States Navy's demanding specifications, the F4U had evolved from a radical concept into one of the war's most feared combat aircraft. Its distinctive inverted gull wing, massive Pratt and Whitney R2800 double Wasp engine, and revolutionary performance characteristics made it instantly recognizable. More importantly, it had achieved something Japanese aviation struggled to match: a balance between speed, firepower, range, and structural strength. The genesis of the Corsair dated to 1938, when the Navy's Bureau of Aeronautics issued a request for a fighter capable of exceeding 400 miles per hour in level flight. This specification alone was revolutionary. At the time, most fighter aircraft struggled to reach 350 miles per hour. The Navy demanded not just speed, but a complete package: low stalling speed for carrier operations, a range of 1,000 miles, heavy armament, and the ability to carry bombs. Chance Vaught's response was audacious. Chief designer Rex Beasel and his team decided to build their aircraft around the largest, most powerful engine available: the Pratt and Whitney R2800 double Wasp. This 18-cylinder, two-row radial engine produced 2,000 horsepower, nearly double that of most contemporary fighters. To harness this power, they designed a massive 13-foot, 4-inch diameter propeller, the largest ever fitted to a fighter aircraft. The engineering challenge was immediate: how to provide ground clearance for such a large propeller while maintaining structural efficiency for carrier operations. The solution became the Corsair's most distinctive feature. Rather than using conventional straight wings, Beisel's team created an inverted gull wing design. The wings angled downward from the fuselage before levelling out, creating a distinctive M shape when viewed from the front. This configuration allowed relatively short landing gear while providing propeller clearance. The anhedral angle where the wing met the fuselage also created optimal aerodynamic conditions, minimizing drag. The prototype XF4U-1 first flew on May 29, 1940, piloted by Lyman A. Bullard Jr., Vaught's chief test pilot, from the factory airfield in Stratford, Connecticut. On October 1, 1940, during a test flight between Stratford and Hartford, the XF4U-1 achieved a ground speed of 405 miles per hour with tailwind assistance, making headlines as the first single-engine American fighter to reach this milestone. The aircraft's actual maximum level flight speed was 378 miles per hour at 23,500 feet, still exceptional performance for 1940. Production F4, U-1. Corsairs began reaching operational units in late 1942. Marine Fighter Squadron FIMF-124 received the first combat-ready aircraft, deploying to Henderson Field, Guadalcanal, on February 12, 1943. the Corsair's combat debut proved inauspicious. On February 14, 1943, during what became known as the St. Valentine's Day Massacre, Corsairs suffered a disastrous first engagement. 9 American aircraft were lost, including 2 Corsairs, multiple P-38 Lightnings, P-40 Warhawks and bombers, while Japanese defenders lost only a single Zero fighter. The 9-to-1 loss ratio in Japan's favour was so severe that daylight bombing missions to Bougainville were suspended pending tactical reassessment. This engagement demonstrated that superior technology alone could not guarantee victory. Tactics, experience, and proper deployment mattered equally. American pilots adapted quickly. They learned that the Corsair's strengths lay not in dogfighting, but in what became known as boom and zoom tactics. The Corsair could not outturn a Zero in slow-speed manoeuvring, but it could outdive, outclimb, and outrun any Japanese fighter. Proper tactics meant maintaining speed and altitude advantage, diving on enemy aircraft, firing, and using superior speed to disengage before the enemy could respond. Second Lieutenant Kenneth A. Walsh of VMF 124 became the first Corsair ace on May 13, 1943, mastering these tactics and eventually achieving 21 victories. As the war progressed through 1943 and 1944, the Corsair's reputation grew. Marine squadrons in the Solomon Islands, flying from hastily constructed coral airstrips, exploited the aircraft's ruggedness to devastating effect. The Corsair proved capable of absorbing battle damage that would have destroyed lighter Japanese fighters. Its 650 caliber Browning machine guns, the 4 inboard guns carrying 400 rounds each, and the 2 outboard guns carrying 375 rounds each, totaling 2,350 rounds, provided overwhelming firepower. Later variants like the F4U replaced the machine guns with 4 20mm cannons, though many pilots preferred the reliability and ammunition capacity of the 50 caliber weapons. The Corsair's versatility extended beyond air combat. By mid-1944, Corsairs regularly carried external ordnance: 1,000-pound bombs on centerline and wing racks, 8 5-inch high-velocity aircraft rockets, or napalm canisters. This fighter-bomber capability made the Corsair invaluable for close air support during amphibious operations. During the Okinawa campaign in 1945, Corsairs flew thousands of ground attack sorties, earning the nickname Angels of Okinawa from grateful infantrymen. What Japanese pilots encountered in combat told only part of the Corsair's story. From the cockpit of a Zero or other Japanese fighter, a pilot saw an opponent that was faster, stronger, and more resilient. But understanding the engineering and manufacturing techniques behind these advantages required physical examination of the aircraft itself. Japan's capability for such technical analysis centered on 2 facilities: the Yokosuka Naval Air Technical Arsenal south of Tokyo, and the Army Aviation Technical Research Institute at Tachikawa. These organizations had been examining captured Allied aircraft throughout the war, recovering examples from battlefields across the Pacific. Their work had provided valuable intelligence about American capabilities, but most captures were damaged aircraft or incomplete wrecks salvaged from crash sites. An intact operational example of a frontline American fighter represented an extraordinary opportunity. The Japanese Navy's Yokosuka facility had been conducting technical research since April 1, 1932, when it was reorganized as the Kaigun Kokusho, Naval Air Arsenal. By World War II, Yokosuka employed thousands of engineers, designers, and technicians. The arsenal designed numerous Japanese naval aircraft, though actual production was contracted to companies like Aichi, Nakajima, and Mitsubishi. Yokosuka's engineers were experienced professionals who understood aircraft design at the highest level. When a salvaged Corsair arrived at Yokosuka in early 1945, it represented one of the most modern American fighters yet recovered in relatively intact condition. The aircraft had suffered water damage during its forced landing, but the basic structure remained sound. Recovery teams had worked to prevent complete sinking, and the fighter was transported to Yokosuka's secure technical area for examination. Initial assessment focused on overall condition. Despite saltwater immersion, much of the Corsair remained intact. The massive Pratt and Whitney engine would require complete disassembly and cleaning, but the airframe structure showed no combat damage. This was crucial. Previous Allied aircraft captures often involved heavily damaged machines, making it difficult to distinguish design features from battle damage. Japanese specialists began with systematic photography and measurement. Every dimension was recorded: wingspan of 40 feet, 11.7 inches, length of 33 feet, 4 inches, height of 15 feet with wings extended, or 16 feet, 2.3 inches when wings were folded for carrier storage. The inverted gull wing configuration immediately drew attention. Japanese designers understood the aerodynamic and structural advantages of this design, but they also recognized its manufacturing complexity. Creating the compound curves and maintaining precise angles required sophisticated tooling and quality control beyond what most Japanese factories could achieve reliably at this stage of the war. The examination revealed something that particularly surprised the technical team. Despite the Corsair's advanced nature, portions of its outer wing surfaces were covered with fabric rather than metal. Aft of the main wing spar and armament bays, both upper and lower surfaces used fabric covering, as did the control surfaces, ailerons, elevators, and rudder. Japanese aviation specialists initially found this puzzling. By 1944 to 1945, most modern fighters used all-metal construction. Further analysis revealed a sophisticated reality. The fabric covering was a deliberate design choice from the aircraft's 1938 to 1940 development period. It reduced weight where structural loads were minimal, saving aluminum for critical load-bearing components. The fabric was specially treated material that, when properly applied, provided adequate strength and weatherproofing while weighing significantly less than metal skinning. This represented mature understanding of resource allocation for optimal performance. Disassembly of the wing structure revealed construction methods that technical personnel found both impressive and troubling. The main wing spar, the critical structural element carrying flight loads, was a massive forging of exceptional quality. American metallurgy had produced aluminum alloy forgings with strength characteristics Japanese facilities struggled to match. The spar's dimensions and load-bearing capacity exceeded anything in comparable Japanese fighters. This single component illustrated a fundamental difference. American industry could produce large, complex forgings with consistent quality, while Japanese manufacturers increasingly relied on built-up structures assembled from smaller components. The wing's internal structure demonstrated similar sophistication. Ribs, stamped from aluminum sheet, showed remarkable precision and consistency. Each rib was virtually identical to the next, indicating manufacturing processes with tight quality control. Japanese aircraft production increasingly struggled with consistency as the war progressed, with individual aircraft showing variations in component quality. Attention turned to the Corsair's armament installation. 6 Browning A&M 250 caliber machine guns mounted in the wings represented formidable firepower. The installation was compact, reliable, and designed for easy maintenance. What struck Japanese examiners was not just the firepower, but the system's completeness. Ammunition boxes, feed systems, spent cartridge ejection, and charging mechanisms were all engineered to work seamlessly together. The guns themselves were specimens of precision manufacturing. American ordnance production had achieved reliability levels Japanese industry envied. The Browning M2 machine gun was a mature design, perfected through decades of development and manufactured by the millions with extraordinary consistency. Japanese technicians examining these weapons recognized manufacturing techniques and quality standards their own factories could not consistently achieve. The discovery of 150 pounds of armor plate protecting the cockpit and a 1.5-inch thick bullet-resistant glass panel behind the windscreen reinforced impressions of American design philosophy. Japanese fighters had largely abandoned heavy armor protection in favor of lighter weight and better maneuverability. The Zero's early success seemed to validate this approach. But as American fighters grew more powerful and better armed, the lack of protection became fatal. The Corsair demonstrated that proper engineering could incorporate substantial protective armor without sacrificing performance, made possible by the massive power of the R2800 engine. That engine dominated the technical examination. The Pratt and Whitney R2800 double Wasp represented American aero engine development at its peak. 18 cylinders arranged in 2 rows of 9, displacing 2,800 cubic inches and producing over 2,000 horsepower. This engine was a masterpiece of mechanical engineering. Japanese engineers had encountered this engine before in captured aircraft, but never had they possessed an example in relatively good condition for thorough analysis. The engine's construction revealed manufacturing capabilities that seemed almost incomprehensible. Cylinders were precisely machined with tolerances measured in thousandths of an inch. Pistons, connecting rods, and crankshaft components showed surface finishes and dimensional accuracy that Japanese engine manufacturers struggled to achieve. The two-stage supercharger system, designed to maintain power at high altitudes, incorporated complex internal passages and precisely fitted rotating components. Japanese attempts to develop comparable supercharger systems had largely failed due to manufacturing limitations. Perhaps most impressive was the engine's reliability and power output. American radial engines routinely produced their rated horsepower for hundreds of hours between overhauls. Japanese engines, even new examples, often failed to achieve their theoretical power ratings and required frequent maintenance. The R2800's consistent performance came from superior metallurgy, better lubricants, more precise manufacturing, and more sophisticated quality control. The propeller system proved equally revealing. The Hamilton Standard hydromatic propeller, with its 13-foot 4-inch diameter and variable pitch capability, represented advanced aerodynamic design and hydraulic control systems. Japanese engineers understood propeller theory, but lacked manufacturing facilities capable of producing large propellers with necessary precision. Examination of systems throughout the aircraft revealed consistent patterns. The landing gear mechanism was complex but precisely manufactured. The cockpit instrument panel presented comprehensive arrays of gauges and controls exceeding anything in Japanese fighters. The fuel system incorporated self-sealing tanks using multiple rubber compound layers that swelled when punctured, preventing catastrophic fuel loss. Technology Japanese aircraft largely lacked. The electrical system powered extensive equipment through high-quality wiring with proper insulation and organization. Perhaps most revealing was the overall quality of materials and manufacturing. Every component, from major structural elements to small fasteners, showed consistent quality. Aluminum alloys had uniform properties. Steels were properly heat-treated. Surface finishes were smooth and professional. The aircraft felt substantial, well-made, built to last. This overall quality stood in sharp contrast to Japanese aircraft production in 1945. Wartime shortages had forced increasing use of substitute materials. Aluminum quality had deteriorated. Skilled workers had been conscripted. Factories operated under constant threat of American air raids. Quality control suffered as production schedules demanded quantity over quality. The examination of the captured Corsair occurred as Japan faced imminent defeat. American B-29 bombers were systematically destroying Japanese cities. The Navy had been shattered at Leyte Gulf. The Philippines had been liberated, Iwo Jima had fallen, and Okinawa was under assault. In this desperate context, the Corsair examination took on somber significance. It was not intelligence gathering for future victories, but a final reckoning with technological reality. Japanese engineers at Yokosuka and Tachikawa wrote technical reports documenting their findings. These reports detailed measurements, described manufacturing techniques, and offered assessments of American capabilities. The tone was professional but could not hide underlying implications. In nearly every category examined, American technology exceeded Japanese capabilities. The gap was not small or easily closed. It represented years of industrial development, massive investments in research and tooling, sophisticated supply chains, and resources Japan simply did not possess. By war's end, in August 1945, at least 2 Corsairs had been captured by Japanese forces. Evidence suggests technical personnel repaired at least one aircraft toward flying condition, as photographs show captured Corsairs with patched wings and fuselages. Whether actual flight testing occurred remains uncertain, but repair attempts indicate serious efforts to make aircraft operational for evaluation. When American occupation forces arrived at Yokosuka Naval Air Technical Arsenal in September 1945, they found extensive evidence of Japanese technical intelligence efforts. Captured Allied aircraft were scattered around the facility. Technical reports, drawings, and photographs documented Japanese attempts to understand Allied technology. American intelligence officers collected these materials, recognizing their value for understanding what Japan had learned. The story of Japanese examination of the F4U Corsair represents more than technical intelligence. It symbolizes the vast gulf separating American and Japanese aviation by war's end. When the Corsair first entered combat in early 1943, Japanese pilots in Zero fighters could still compete effectively through superior tactics and pilot skill. By 1945, even experienced Japanese pilots in more modern aircraft stood little chance against well-flown Corsairs. The aircraft's technological advantages, combined with overwhelming American numerical superiority and better pilot training, created impossible odds. The Corsair achieved an official kill ratio of 11-1 against Japanese aircraft. American pilots flying Corsairs shot down 2,140 Japanese aircraft, while losing only 189 Corsairs to enemy action during World War II. These numbers reflected not just the Corsair's technological superiority, but the entire American war machine's advantages. Better training, superior logistics, overwhelming production capacity, and advanced technology at every level. Japanese engineers examining the captured Corsair understood all of this. They could measure the performance gap, analyze the manufacturing differences, and calculate the resource disparities. Their reports documenting these findings stand as acknowledgements of Japan's failed attempt to match American industrial might. The Corsair itself went on to long service beyond World War II. It fought in the Korean War from 1950 to 1953, where it proved effective in ground attack and close air support roles, even as jet fighters took over air superiority missions. Foreign air forces, including France, flew Corsairs in colonial conflicts through the 1960s. The last combat missions by Corsairs occurred in July 1969 during the brief soccer war between Honduras and El Salvador. On July 17, 1969, Honduran Captain Fernando Soto, flying an F4U-5, shot down 3 Salvadoran aircraft, including 2 FG-1D Corsairs, the final combat victories for the type, ironically achieved against other Corsairs. From its first flight in 1940 to its final combat missions nearly 30 years later, the Corsair proved one of aviation history's most successful and long-lived fighter designs. For Japan, the encounter with the Corsair was part of a larger reckoning with technological reality during the American occupation. Japanese engineers and scientists who had struggled against material shortages and industrial limitations during the war now worked with American occupation authorities to rebuild Japanese industry. Lessons learned from examining American technology, including the Corsair, influenced post-war Japanese manufacturing philosophy. The emphasis on quality, precision manufacturing, and continuous improvement that characterizes modern Japanese industry has roots in the hard lessons learned when Japanese engineers examined what American industry could produce. The Corsair recovered in early 1945 represented more than a downed fighter. It was evidence of engineering excellence and manufacturing sophistication that Japanese aviation had been seeking throughout the war. The lessons it taught came too late to change the war's outcome, but they helped shape the peace that followed. In examining this American fighter, Japanese engineers confronted the full magnitude of the challenge Japan had faced. They had fought with courage and skill, but courage and skill could not overcome the massive technological and industrial advantages their opponent possessed. The story ends not with triumph, but with acknowledgement. Japanese technical reports on the Corsair, discovered by American occupation forces and now resting in archives, serve as silent witnesses to a moment when one nation's engineers confronted another nation's capabilities. The Corsair they examined has long since vanished, likely scrapped during the chaotic post-war period. But its legacy remains in the lessons it taught about what technology, properly applied with adequate resources and sophisticated manufacturing, could achieve. Japanese aviation would rise again in the post-war era, but never again would Japanese engineers underestimate what their American counterparts could accomplish when given the industrial capacity, scientific knowledge, and resources to fully realize their designs. The examination of the F4U Corsair by Japanese technical personnel in 1945 stands as a watershed moment, the point when Japan's aviation establishment fully grasped the technological chasm that had opened during the war years. It was a lesson written not in propaganda or combat reports, but in aluminum alloys, precision forgings, and manufacturing tolerances that spoke louder than any words could about the true nature of American industrial power.